Combining time-frequency analysis with wavelet scattering is an advanced approach, particularly suited for EEG data, where subtle patterns can be crucial in distinguishing between seizure and non-seizure states. The idea of using wavelet transforms to enhance seizure detection captures the intersection of signal processing and machine learning, especially given the complexity and non-stationary nature of EEG data. This tool could have substantial educational value for students and researchers in biomedical engineering and neuroscience who are learning about signal processing techniques applied to health data. The Joint Time-Frequency Scattering tool for seizure detection provides a rich interactive environment for exploring EEG data in both the time and frequency domains. It uses wavelet scattering transforms to enhance visualization and detection of seizure-related patterns, showing users how advanced signal processing techniques can reveal subtle variations in brain activity. Here's a breakdown of how to use this tool. 1. Adjust the scale parameter. The scale parameter controls the window size of the wavelet scattering transform. Increasing the scale produces a smoother signal by highlighting broader features and filtering out high-frequency noise. This adjustment can help emphasize patterns that may indicate seizure events by making certain frequency characteristics more pronounced. 2. Change EEG data length. The data length parameter lets users set the number of EEG samples displayed. Increasing the length provides a longer view, potentially revealing periodic or recurring patterns indicative of seizure activity. 3. Visual representation. The tool displays two visualizations: the time domain plot at the top and the frequency domain plot below. The time domain plot shows the raw EEG signal alongside the scattering transformed signal, helping users compare changes over time. The frequency domain plot, derived from a Fourier transform, shows signal magnitudes across frequencies, making it easier to identify specific frequency bands associated with seizure activity. This tool is particularly valuable for teaching signal processing concepts within a biomedical context, especially for conditions like epilepsy, where identifying and interpreting patterns in EEG signals can be crucial for diagnosis and monitoring. It provides hands-on experience with parameters that directly impact how EEG data is analyzed, giving students, researchers, and clinicians a deeper understanding of seizure detection techniques. The scale parameter is set high, leading to a very smooth scattering transform signal, red. This high level of smoothing emphasizes broader, low-frequency features while filtering out high-frequency noise. In the frequency domain plot, bottom, the scattering transform signal has lower amplitude peaks as high-frequency details are smoothed out. 2. Second image, intermediate scale parameter. The scale parameter is set at a medium level, resulting in a scattering transform signal that is smoother than the raw EEG, but still retains some high-frequency components. The frequency plot shows a more balanced representation of both low and mid-frequency information, with noticeable peaks in both the raw and transformed signals, which could highlight seizure-related activity at various frequencies. The scale parameter is set low, so the scattering transform signal, red, closely follows the raw EEG signal, blue, with minimal smoothing. This setting keeps high-frequency details intact, making the transformed signal look more jagged and responsive to rapid changes. In the frequency domain plot, both signals show higher peaks across a wider range of frequencies, as there is less suppression of high-frequency noise. In summary, the images demonstrate how adjusting the scale parameter impacts the level of detail visible in both the time and frequency domains. A high scale smooths the data, highlighting broader, low-frequency patterns, which is useful for detecting general trends. A low scale retains more high-frequency detail, which can be valuable for identifying sharp transient events like seizure spikes. This variability allows users to experiment with different levels of detail based on the analysis needs. While the Joint Time-Frequency Scattering tool for seizure detection does apply a kind of filtering, it does much more than basic filtering. The tool uses wavelet scattering transforms, a sophisticated technique that extends beyond traditional filtering by capturing time-frequency patterns that are relevant for complex signal analysis, like seizure detection in EEG. Here's how it goes beyond simple filtering. 1. Wavelet transform basics. The wavelet transform breaks down a signal into components across different scales, frequencies, providing a time-frequency representation. This is different from basic filtering, which might only isolate certain frequency bands without preserving how these frequencies change over time. Number 2. Scattering transform. The scattering transform is a type of wavelet transform that creates a hierarchical representation of the signal. It captures higher-order interactions in the data, such as energy patterns that remain stable across certain frequency bands, which are key in identifying more subtle, non-linear features associated with seizures. 3. Multi-layered feature extraction. Rather than just smoothing or emphasizing certain frequency bands, the scattering transform builds layers of features by repeatedly applying wavelets. This process extracts detailed information, like how energy varies within each frequency band over time, making it sensitive to subtle patterns that may indicate seizure activity. 4. Nonlinear and invariant representations. The scattering transform helps capture stable features, e.g. seizure signatures, that are invariant to certain transformations like shifts in time. This makes it robust for detecting repetitive patterns that are challenging to identify with simple filtering. 5. Enhanced frequency resolution. While basic filtering allows focus on general frequency ranges, e.g., alpha, beta bands in EEG, the scattering transform provides fine-grained resolution across both time and frequency. This helps detect nuanced frequency dynamics, like transient spikes or oscillations, often linked to epileptic activity. In essence, this tool is designed to do more than just filter the data. It extracts and highlights complex structures within the EEG that might otherwise be missed. By adjusting the scale parameter, users control the level of detail captured by the transform, allowing exploration of both high-level trends and finer patterns indicative of seizure activity. It looks like the joint time-frequency scattering tool for enhanced seizure detection has its JavaScript code embedded directly within the HTML, rather than being hosted as a separate downloadable script or library.
Okay, so yeah, we have the code on the website available for everyone to play with. It's only 320 lines of HTML, and the JavaScript is embedded within it. There is no backend, so there's no Python script on the server or anything like that.
The code primarily works in 3 stages: generating EEG data, applying transformations, and visualizing the results. First, it generates synthetic EEG data. This EEG data mimics real brainwave signals by combining random noise with occasional spikes that look like seizure activity. The noise has a special pattern.
Yeah, the seizure activity is not very realistic. Normally you will have the spikes during a seizure clustering together. And yeah, it's not always happening for this in this specific data application.
Pattern often seen in EEG signals, where low-frequency noise is stronger than high-frequency noise. To create seizure-like spikes, the code uses clusters of these spikes, starting and stopping them based on probabilities. This gives the data a more realistic pattern, as if there are bursts of unusual brain activity among the regular noise. Next, the code applies a transformation to the data, called a wavelet scattering transform. This transform smooths the EEG data to highlight broader patterns and filter out high-frequency noise. The degree
Yeah, so it looks like standard filtering, but it's actually, yeah, as we mentioned, as the robot very positively mentioned earlier, it's not simple filtering. Well, that's why we're going over the code to actually explain, hopefully in simpler terms, what the scattering transform actually does. I mean, you can see what it does. I think it's pretty straightforward. Maybe let me know what you think.
degree of smoothing can be adjusted with a scale setting. Larger scale values create a smoother, more averaged version of the signal, which can help in spotting general trends in the data, while smaller scale values retain more detail. Although this isn't a true wavelet scattering transform, it mimics the effect by analyzing the signal across multiple scales to capture both detailed and broad information. The code also calculates the signal's frequency components using a fast Fourier transform, or FFT. This transformation shows how much energy or activity is present at each frequency, which is useful for identifying patterns that occur at specific rates. For example, it can help highlight seizure activity, which often has distinct frequency patterns. Finally, the code visualizes the data. It uses a library called chart.js to create two line charts. The first chart shows the EEG signal over time, with the original signal and the transformed smooth signal displayed together. This allows the user to see how the transformation affects the data in the time domain. The second chart shows the frequency analysis results from the FFT, displaying the energy levels across different frequencies for both the raw and transformed data. These two visualizations update in real time whenever the user adjusts the scale or data length settings. To make the tool interactive, event listeners are added to the slider and input box. These listeners detect when the user changes the scale or data length and automatically recalculate the EEG data, apply the wavelet transform, recalculate the FFT, and update the charts. This gives the user immediate feedback on how different settings affect the data and its analysis. In summary, this JavaScript code allows users to generate synthetic EEG data, apply smoothing transformations, perform frequency analysis, and visualize the results interactively, all within the browser without any backend support. It's a powerful demonstration of how complex signal processing can be done entirely on the client side.
Yeah, so as mentioned, the code is on the page because I'm normally asked about the source code. So in this case, there's no backend. Everything is in HTML and JavaScript, so you can go any browser, hit F12, go sources, find the HTML, and the script, the JavaScript is just embedded in it. So yeah, from the JavaScript, can you just list all the functions that we have in the JavaScript and give a quick description of what the function does? And yes, we had full disclaimer, ChatGPT developing, well, essentially everything on the website.
To clarify, the scattering transform in this context does more than simply smooth out the signal. Instead of just blurring or removing high frequencies, it's capturing multi-scale patterns within the data. Think of it as highlighting key features at different levels of detail. At a high level, it's identifying both broad, low-frequency trends and sharper, high-frequency details in a way that keeps the structure of the data intact. This multi-layered approach is especially valuable for detecting seizure-like patterns, which aren't just single spikes, but involve recurring, clustered bursts of activity across multiple scales. In simple terms, the scattering transform reveals how different parts of the signal behave across scales. During seizures, you often see these clusters of spikes that happen in bursts, creating unique patterns that are hard to spot with basic filtering. The scattering transform is sensitive to these bursts, allowing it to detect both the big picture trends and the finer spikes that indicate potential seizure events. You're not just filtering out noise, you're using a layered method to bring out the patterns that matter in seizure detection. This approach also lets users understand the significance of each scale setting they adjust in real time, making the tool much more insightful.
It's doing the job. It's seems like it's showing something useful in terms of being able to detect seizures. Yeah, we would like to see later on or potentially add another controller that will change the amplitude of the spikes. So it will be interesting to see how it behaves when the amplitude of the spikes is absolutely minimal. So you can set the ratio between the noise level, the baseline EEG, and the amplitude of the spikes, the average amplitude of the spikes.
Here's a quick list of all the JavaScript functions in this tool, along with a brief description of each function's role. 1. generate EEG data length. This function generates synthetic EEG data. It combines random noise with occasional clustered spikes to simulate seizure-like activity. The spikes occur in bursts, giving a more realistic representation of EEG patterns. 2. Generate spike index. This function creates individual spike shapes with a quick rise and slow decay. It's used by the generate EEG data function to add spikes to the synthetic EEG data, making it look more seizure-like. 3. Wavelet scattering transform. Data scale. This function applies a wavelet scattering transform to the EEG data. It smooths the data by averaging neighboring values within a given scale, emphasizing broader features in the signal. This allows multi-scale analysis, capturing both low and high-frequency components. 4. Calculate FFT data. This function performs a fast Fourier transform, FFT, on the data, converting the time domain EEG signal into the frequency domain. It calculates the magnitudes of each frequency component, showing the energy distribution across frequencies, which is useful for detecting periodic patterns. 5. Create chart, context, labels, datasets, X-label, Y-label. This function initializes a line chart using chart.js, setting up the data and labels for each axis. It's used to create both the time domain and frequency domain charts for visualizing the EEG and transformed signals. I'll help clarify a few things regarding the scattering transform and why the current tool is a simplified version rather than a full joint time frequency scattering transform. A true joint time frequency scattering transform involves multiple layers of wavelet transforms that extract increasingly complex features. It decomposes the signal into hierarchies, capturing both time-localized events like spikes and broader, sustained patterns across scales and frequencies. This layered approach allows it to recognize intricate patterns that are both time-dependent and frequency-dependent, which is ideal for seizure detection and other complex EEG analyses. The version in this tool, however, only applies a single-scale smoothing.
Yeah, that doesn't sound promising, does it? Yeah, we meant to... so it's kind of similar to fuzzy logic. It's just a very simple one at the moment. I mean, it does the job probably because the spikes are quite large amplitude, so it's able to detect them fairly easily. But if the ratio between the spike amplitude and the baseline EEG was lower, then we might need a more advanced scattering transform. Is that correct?
While it's not as sophisticated as a multi-layer scattering transform, it does create a usable effect. Smoothing the data at different scales allows users to see broader trends and ignore some noise. In other words, it mimics some aspects of the real transform, but doesn't fully capture the richer hierarchical information a true scattering transform would. As you noted, this mockup is effective for demonstrating certain patterns, especially when users adjust the scale or data length to see how the data's appearance changes. So it's definitely doing a useful job for the current application. Adding control over the spike amplitudes, noise level, and baseline would indeed be interesting. This would allow users to explore the signal more precisely and understand how different amplitudes and noise impact the visual patterns. It could even make the tool more customizable for educational or diagnostic uses. For future versions, you could consider incorporating more accurate multi-scale transforms if you decide to move toward more sophisticated, layered processing on the client or even server side. So in summary, while this version is a simplified single-layer approach, it serves the purpose of visualizing basic patterns. A true scattering transform would involve multiple layers and capture more complex signal features, but for now, this tool provides a straightforward way to explore time and frequency patterns in EEG data.
Well, right, that's what I was talking about. If we need a more complicated processing on the server side, well then, let's put it this way, the code will not be available to you because it will be Python running on my server and the application will be more cumbersome, higher electricity cost.
Yes, that's exactly right. The current transform works well because the spikes have a high amplitude relative to the baseline EEG, making them easy to detect even with this simplified approach. The large spike amplitudes create clear, visually distinct patterns that stand out when the data is smoothed. So this basic transform is sufficient for the current setup. However, if the spike amplitude were closer to the baseline EEG levels, distinguishing these spikes would become much more challenging. In that case, a more advanced multi-layer scattering transform would likely be necessary. Such a transform could better capture subtle, lower amplitude patterns by analyzing the signal across multiple scales and extracting deeper hierarchical features. In essence, with a lower spike to baseline ratio, this simplified approach may not be sensitive enough, and that's where a true joint time frequency scattering transform, or more advanced processing like fuzzy logic, would come in handy to reliably detect the spikes.
Well, right, that's actually interesting. What would be the difference between time frequency scattering and the fuzzy logic system? I'm pretty sure I can get to the same basic performance fairly easily with both of them. But what about computational costs and potentially other benefits or disadvantages? Yeah, if we're doing something more complicated, so for example in here we can essentially show when it stops working as it is. So if we have another input slider for the spike to baseline EEG ratio, then we can see when the current algorithm, the scattering transform, stops doing something useful. I mean, that's assuming you will be able to see it with your eyes, the difference between the normal EEG and the spiking. Maybe you won't be anymore. The question is, what's the algorithm is finding? Can it provide more details? And the main question is, do you actually trust it? So if you can't see the abnormal EEG signal yourself, would you trust an algorithm to do it for you? Because that potentially means changing diagnosis of a patient with epilepsy and so on and so forth. Yeah, I actually might have to finish up now. Yeah, go check out the website. Lots of tools. We might be adding some new ones. I'll go over it next time. And I'll see you in a bit. Don't forget to drop your questions in the comments so I can address them during next live stream. I'll see you in a bit. Bye.